second part of our program. The headline is Automation, Inequality, and Productivity. As you know, the first part of this presentation was in Turkish. Because of that reason, I will give you some information about Professor Acemoğlu in English. Briefly, he completed his undergraduate education in University of York in the area of Departments of Economics. Then he completed his master degree in London School of Economics. The area is, as you can see, mathematical economics and econometrics, and he completed in the same university, London School of Economics, in the PhD, economics field. Then I would like to give you some information about him. Just a moment. About his work experience, as you can see, he started after his PhD education as a lecturer in the same university. I'm talking about London School of Economics in here. Then he attended MIT as an assistant professor. He continued his work experience. I'm talking about academic experience, of course, as an assistant professor, associate professor, and professor of economics in the same university. He's currently working as institute professor in departments of economics at MIT again. And when we look his academic areas, actually he has very broad areas in economics, including, you will see, political economy, economic development and economic growth, human capital theory, growth theory, search theory, and network economics and learning. And when we look his books, he's the author of 6 main books in the field. He wrote too many books in our field. One of them with James Robinson, Economic Origins of Dictatorship and Democracy. The second one is Introduction to Modern Economic Growth. And the last one is Why Nations Fail, The Origins of Power, Prosperity and Poverty. As we know, with this book, Professor Acemoğlu and Robinson received too many awards from different societies. Meanwhile, he wrote with James Robinson, The Narrow Corridor. With David Leibson and John List, he wrote a book, the name is Principles of Economics. And then his last book, in the first part of today's actually events, we saw in Turkish part, Power and Progress. We listened his evaluations about his book, you can remember in the first part. And when we look at his fellowships, actually he's elected too many important societies. You can see National Academy of Sciences, British Academy, American Philosophical Society, Turkish Academy of Sciences, Society of Labor Economics, Econometric Society. There are too many. I showed just some of them actually. And when we look some awards of him, Schultz Prize, John Bates Clark Medal, John von Neumann Award, Irving Klein Nemers Prize. Actually, in the first part, as you can remember, our rector said that why did the Economic Society give the Nobel to Professor Acemoğlu? I agree with our rector, actually. When we look at, for example, Irving Klein Nemers, it's the most prestigious, one of the most prestigious prize in our area. And when we look at Jean-Jacques Lafont and Turkish Academy Prize, we saw. And of course, the last part of my presentation to give some information about Professor Acemoğlu. Utrecht University, Boğaziçi University, University of Athens, Bilkent University, University of Bath, Scully Paris, London Business School, and today he received from our university honorary professorship. Okay. I'm very exciting as an economist. I would like to introduce and invite stage for his academic presentation, Automation, Inequality, and I would like to introduce Professor Acemoğlu. Thank you.
Kurtaralım biraz. Ha, tamam. Ha, teşekkürler, sağ olun. Çok teşekkürler. Çok sağ olun. Bu ikinci bölüme geldiğiniz için çok teşekkürler. İngilizceye geçeceğim ama öncelikle Türkçe olarak söyleyeyim. Hepinize vaktinizi ayırdığınız için çok teşekkürler ve ayrıca ne yazık ki bu biraz daha teknik, doktora öğrencisi düzeyinde bir konuşma. Olabildiğince basit anlatmaya çalışacağım ama bazı bölümleri ne yazık ki daha teknik. Okay. So I'm gonna summarize some recent advances in the area of the impact of technology on inequality, wages, and productivity. And the reason for doing this is, A, there has been a major transformation in how the labor market works, which types of skills are being rewarded, how the wage structure looks like, and how productivity gains are accruing and which groups they are accruing to. And the research I'm going to summarize comes out of the belief that existing frameworks, which are extremely common, people learn in undergraduate economics and certainly in graduate education, are thoroughly inadequate for making sense of the current changes. And in fact, this inadequacy reflects a broader set of limitations of current approaches. So it's a kind of alternative framework, alternative new framework for making sense of things. And to get you going, here is the same picture as I showed in my first talk, the evolution of inequality after a period of about 30 years where you had shared prosperity, where real wages across demographic groups were growing in tandem and growing at the same rate as productivity growth in the United States, about between 2 and 2.5% a year in real terms. You have three associated, oops, what happened? Oops, okay. You have three associated changes. One, a huge increase in inequality, the top and the bottom diverging. Second, and relatedly, median wages or average wages now falling far short of productivity growth. So overall, labor's income is not growing on average as fast as aggregate productivity. And third, the real wages of low education groups are actually declining in real terms quite significantly, as you can see, for example, from the pink or the gray lines for high school dropouts and high school graduates. And these facts are beyond doubt. The interpretation is not a complete consensus, but the facts are quite broadly accepted, and they are present in a variety of different data sets. And in fact, in this figure, I'm showing it both from the American Community Survey and the US decennial censuses, but you can also see it in other data sets. As a consequence of the second fact that I mentioned, which is that labor income is growing more slowly than productivity, you also see that labor share of national income is declining quite significantly. The black dots there is for the entire US economy. You see that the US labor share was about 2/3 and has come down to about 0.6, so about a 8 to 9 percentage point. But especially in manufacturing, which is the yellow, there has been a complete collapse of the labor share in manufacturing. Manufacturing, even though has a lot of investment in capital, has traditionally been a very labor-intensive industry. So about 70% of value added in manufacturing used to accrue to labor, and that has fallen in the course of about 20 years to just over 45%. So it's a complete collapse of how much of the resources go to labor. Also associated with oops, what's going on here? Also associated with these wage and payment related facts is a set of other changes in the labor market. Employment rates are also changing, but I'll come back to those in a little bit. But the more important one that I want to sort of mention now to frame the discussion is that the occupational structure is changing. So in particular here, what I'm showing you is the share of routine occupations in what different demographic groups do. So in particular, if you look at the beginning of the sample in the 1960s, low education workers, those with a high school degree or less than high school, were performing a lot of jobs that we classify, in my past work with David Otter, I classified, and David Otter himself in some of these other work classified as routine jobs. They are jobs that are relatively easy to describe as a number of procedures. And the reason why the routine is a relevant thing is because most machines, until artificial intelligence, aim and sometimes successfully do automate routine jobs. So for example, assembly is, it follows a very predictable set of rules. You assemble different pieces in the same way, especially in standardized production. That's a routine job that a well-designed machine, actually computer numerical control machinery, but even robotics today, can actually perform these tasks. So you see that the fraction of the labor force that perform routine tasks either in offices or on factory floors was about 40% in these low education groups and fell to around 15%. And notably, of course, this less routine structure, because these jobs are being taken over by machines, is not affecting the high education groups all that much, because they didn't perform these routine jobs. They were more likely to be managers or engineers, which are not, according to this definition, routine, because they are dealing with more variegated decision-making problems. So what I'm going to talk about is how to understand these changes, in particular, putting under the spotlight the effects of technological developments. Of course, my discussion is already framing that. I'm drawing a link between what's going on in the wage domain to the changes in these routine occupations, which, as I highlighted, is related to some of these routine jobs being taken over by machines or algorithms. So that's a sort of a technology story. It doesn't deny other factors such as institutions, globalization, and so on, but I'm gonna put the focus mostly on technology. So to motivate what I'm going to do, or what I'm going to present, which is like a graduate lecture actually, so I'm taking for granted a lot of knowledge of technical economics. I apologize for those of you who are here from a more broader background, but just to give you a little bit of a summary is that, most graduate students and most advanced students in any institution learns about the interaction between technology and the labor market and technology and productivity by positing what economists call an aggregate production function. So what this says is that, if you want to produce some output, you combine different types of factors of production. In particular, let me do this with two types of factors of production: L for low-skilled workers like high school graduates, H for more high-skilled workers such as college graduates. And then we try to understand productivity as these what are called factor augmenting technologies, meaning technology multiplies factors, it augments factors. So this is sort of very, very canonical. It's, if you went to any advanced undergraduate or graduate course, 99% of what you learn will be this. So the problem is this lacks both descriptive realism, and it doesn't get to grips with the set of phenomena that we want to talk about. It lacks descriptive realism because if you actually look at the production process, a lot of the production process is much more interesting at the micro level. There are a lot of little things that are being done. So this is what we call them tasks. To Turkish, we translate it as ish. I couldn't find a better word for task. But tasks are the little constituent components of production. So for example, if you want to produce an iPhone, think about what it would take for that iPhone to be produced and to reach the hands of a consumer. So you have to start with design and lots of innovative tasks. How to take some functions that exist there already, like for example, menu-driven things, batteries, miniaturized components such as RAM, memory, hard disk, and so on. How to design them in a different form. Some of them actually how to improve them to make them even smaller. What sort of functionality you want to achieve. So these design tasks are actually about 50% of the value added of iPhone production. Then you have to produce each one of these components. The screen has to be produced, the sensors, about thousands of sensors in a regular iPhone, not thousands, but dozens of sensors in a regular iPhone, for example. The battery, the memory chips, the fast access part of the computer. These then have to be produced, then they have to be assembled, they have to be packaged, then they have to be shipped to wholesalers. Wholesalers have to process them and pass them to retailers. Then there's marketing, promotion, advertising, and then finally it reaches the hands of the consumer. So each one of these tasks have to be completed, and it's the aggregation of these tasks that makes the iPhone become a reality. And technology is about the production of these components. What technology does is that it makes some tasks easier to perform by some factors. So for example, if I invent a new precision drill, I can make it easier for a worker to screw some pieces together to do the assembly. If it was capital, it's not going to help it. It's not, if it's an engineer, that's not going to be very helpful, or a manager, it's not going to be very helpful. And if the same worker wanted to work in retail, that drill wouldn't be much more useful to him. So it's very micro level that technology works. But more importantly, technology does something that's either not allowed or hidden in this standard reduced form. It reallocates tasks from one factor to another. So what is automation? I'm going to conceptualize automation as technologies that enable the assignment of certain tasks to capital or specialized machinery rather than labor. So robotics was a revolution because before robotics, certain very simple tasks were automated with numerical control machinery. But most of assembly, painting, welding on the factory floor couldn't be done by machines. So robotics suddenly enabled that, and that was a complete reassignment of tasks away from labor to capital. And the other thing, which again I emphasized this morning, is the creation of new tasks. So iPhone is very different from the older style Nokia phones. There's a lot of design and innovation going on, but if you actually look at the production process, there are a lot of new tasks in the production process as well. So this is yet another dimension of technology's impact on productivity, and we'll see on wages and the distribution of output between different factors of production. So we're going to see that, well, it's obvious, I'm not going to actually dwell on it. If you want to understand all these different forms of technological progress, all you can do in the standard one is put them as either AL or AH. They increase either the productivity of low-skilled labor or high-skilled labor. Whereas my description suggests that this is not going to be a very descriptively realistic thing to do. What I'm going to show you is even more than that. You'll actually get the wrong results if you look at the technology through the lenses of an aggregate production function. You won't understand its rich effects. Another aspect that I want to emphasize, which again matters greatly, again, this is sort of graduate PhD level course material, but hopefully it's not unintuitive. If you actually look at this thing here, what matters greatly is what's called the elasticity of substitution between these two factors of production, which means how easily can I substitute one factor for another. So if high-skilled labor becomes very expensive, can I get low-skilled labor to do some of what it was doing before? So typically that takes a very, very reduced form way. For example, a constant elasticity of substitution in this aggregate production function. What I'm going to show you is that if you take a task-based approach, that becomes not just an endogenous object, but in a much more rich endogenous object. It will depend on exactly what's being automated, what's not being automated, what new tasks are being created, and where you're in the production process you are. And we're going to see that different technologies are created very differently. Some of them are going to have big TFP effects, total factor productivity effect, increasing the productivity of all factors of production, whereas some of them are going to have big distributional effects. Okay, all right. So I'm not going to explain the literature because that's not, my purpose here. But this is drawing a lot on my own work with Pasquale Restrepo, which I've been doing for the last 10 years, and also on originally by work by Yossi Zeira, some work I did with Fabrizio Zilibotti, some work that my co-author David Otter did with Livia Murnane and Michael Hendel, and a paper I wrote about 12 years ago, 13 years ago with David Otter myself. All right, so the math here is just putting what I said in words and making it a little bit more precise. So this one is output in a one-sector economy, just only one good. This economy just produces iPhones. The framework I have has made multiple goods, but I'm not going to go into the mathematical details of that. It doesn't deepen your understanding much. It just adds a little bit of notation. So let's just imagine we just produce iPhones, and all of these things that I listed earlier, those are the task services. So X denotes tasks, YX is the task services. So if YX is equal to 0 for assembly, that means you're not assembling anything. So that's not good for producing iPhones. YX for some different X would be the design, etc., etc. If your design is faulty, you can still produce iPhones, but they're not going to generate as much value. So then these are aggregated. So this lambda here is an elasticity of substitution, and they are aggregated with this constant elasticity form. Doesn't matter, it just makes things easier. And since I'm going to emphasize that macroeconomic elasticities of substitution are endogenous and rich, taking the microeconomic one between task elasticity of substitution a constant is both a simplification and helps transparency. So this is how you produce output. You combine task services and you produce output. So if you have a sort of some operations research models would have this structure. So if you want to have like this throughput structure where it's the lowest task service that determines everything, that would be this aggregator takes the form min. That's the special case where this lambda is equal to 0. So this is a more general version of that. The key is how are these tasks combined? And I assume that there are G types of labor, like for example, the 10 types of labor that I showed you earlier on, distinguished by gender and education, and capital, which corresponds to specialized machinery. You might have a computer numerical control. You might have a software system for inventory control or word processing or artificial intelligence. And there's going to be that I'm going to denote that by KX, capital of type X. And rather than take the capital stock as given, I'm going to assume capital is itself produced from the final good. And I'm going to denote the supply of labor of type L by LG. And this production function here says you can produce output, you can produce task services for task X using any one of these factors, but they all have different productivity. So in other words, there is a comparative advantage. Psi gx is the productivity of type X labor in task X. Sorry, type G labor in task X. So for example, if the task at hand is design and type of labor is high school, less than high school workers, their productivity may not be very high, because for design, you need to have knowledge about engineering, high level knowledge, and so on and so forth. Some of these psi g's can be zero, which means that type of labor cannot produce that task. And in particular, psi kx can be zero for tasks that are not technologically automated yet. So if you look at the productivity of capital in doing welding in 1980, that was zero. There's no way that any machine could do welding by itself. You needed to combine that, or you needed to assign that task to some type of labor. And then in addition, I allow for this factor augmenting AKAG type of productivity to contrast the effects of these classic augmenting types of technologies to the task level, especially automation and new task type things. Okay. All right. So the way that economic models work is you specify the environment, which I did in one slide, which is the task production, which is the aggregate, the sectoral production function, task production function. I specified supply of these factors, fixed supply for different types of labor, and capital produced. And then you have a notion of equilibrium. This is a very micro model, but a standard notion of competitive equilibrium works here. In some of my work with Pasquale Restrepo, we consider non-competitive models here. But here, for this one, starting from competitive, which is more standard, is useful to show that that's not where the difference is coming from. It's really the task level specification of these things. So an equilibrium is defined as all tasks are produced in the cheapest possible way and all markets clear. An equilibrium exists and is unique, and it's a very simple characterization. Deriving this is a little bit of work. It's not that obvious, so that's where the innovation of these series of papers was to specify this environment, these new conceptual points, and actually a very tractable and nice characterization. And this characterization really is very much congruent with this microstructure that I've talked about. So the key here, as you can see, is which tasks are going to be assigned to which workers. So that's the key object for the equilibrium as well. So imagine that the task space takes this two-dimensional form. And then imagine there are three factors of production: labor of type G, say high skill, labor of type G prime, low skill, and capital. And an equilibrium looks like a partition. Some tasks are assigned to capital, yellow area. Some tasks are assigned to high skill labor, brown area. Some tasks are assigned to low skill labor, blue area. These tau G, tau K, etc. are sets. They don't need to be connected, but I drew them as connected just for simplicity. But actually their effect can be summarized by a set of objects which Pasquale Restrepo and I call task shares, for reasons that might become obvious to some of you who have played with models like this, why that name is appropriate. And we call these gamma GW, W to emphasize that these task shares are endogenous and they're going to depend on the vector of wages. And they are given by this object. So 1 over M is a normalization. M is the total measure of tasks in the economy. And then you integrate over the productivity of the factor that gets the factor, that task, and you integrate over all set of tasks that are assigned to that factor, where again, I wrote this as tau G of W to emphasize that those sets there that I drew depend on the wage. I'm going to show that in a second, but you can already visualize how, as the factor prices change, those boundaries here are going to shift to the left or to the right. So given these, the theorem here is an equilibrium exists and is unique and has the following characterization. Aggregate output can be written itself as a constant elasticity of substitution aggregator. And those of you who have done graduate economics or mathematical economics, you may have seen constant elasticity production functions. This looks like them. So you take LG, sorry, this shouldn't be X here. LG, the supply of type of labor at a G, multiplied by its productivity. So that's augmented labor, just like in this form here. And then you aggregate it with lambda minus 1 over lambda, like in elasticity of substitution lambda, and you do the same to capital. But except that there are these shares here that I derived here endogenously, multiplying these things. So this looks like a regular constant elasticity of substitution production function, but it's very different from that, precisely because of these endogenous shares. So in particular, it does not, this here is lambda is not the macroeconomic elasticity of substitution, which itself is endogenous. And I'll explain that in a second. And the way that technology is going to affect things is not by changing AK or AG, but it's going to be through changing these task shares. And you can already get an inkling of that if you look at the wages for different demographic groups, different types of skill. WG, the real wage of different groups, is given by a productivity effect, Y over LG, how much output is produced relative to that type of labor. AG here, which is that augmenting term. So if you want to gain simple intuition here in this model, you can also think of lambda is equal to 1. That's the simplest thing, where it's like a multiplicative aggregator, geometric aggregator. In that case, this AG drops out anyway, so that's not where the action is. The action is here. It's all this gamma GW. That's where all the action is going to come from. Okay. By the way, this is more like an academic seminar or lecture, so please feel free to ask questions for comment or clarification as we go along. If I'm going too fast or too slow, also tell me. Okay, so that's the equilibrium, but that's no good to us. That's no good use to us unless we put it to work, and that's what I'm going to do next. So I'm going to show you how this framework gives very interesting new results about the effects of technology, and explain how it changes the way that different factors are substitutes, complements, and their comparative advantage. So in particular, I'm going to show you that in this framework, you can distinguish between two types of technological changes, which I'm going to call intensive margin and extensive margin effects. Intensive margin effects are like this. If I change AG, what I do is I make factor of labor of type G more productive. That's an intensive margin change in the following sense, that it's making that factor more productive in the task that it's already producing. So it's going to create a set of effects because it's going to change the relative abundance of some tasks versus others. But it doesn't have a first order impact on the allocation of tasks between factors. It has a second order effect, which I will explain in a second, but it doesn't have a first order effect. In contrast, what I'm going to call extensive margin changes are those that directly reallocate tasks across factors. Automation and new task creations are the key examples for this. And I'm going to show you that these two types of technologies have hugely different effects. That's the main point that I want to emphasize, and if that's the message that I'm able to deliver, I would be very happy. Yes, please. Yeah, in general, it is endogenous with respect to capital as well. But you know what I did here, I didn't comment on it. I assume that capital is produced one-to-one from the final good. So therefore, its price becomes 1. So then I don't have to keep track of that. But thank you, of course. Wonderful. You also had a question, please? Later? Okay, perfect. All right. The second point that I'm going to make is the rich substitution pattern. And in some sense, if I had optimized this presentation for a broader audience, I would have now dived into explaining this, which is my more important point of emphasis. And I would have skipped this, but I cannot because I didn't do it that way. And I use the notation that I'm going to develop now in explaining this first throughout the presentation. So sorry, I cannot skip the slightly more advanced material. But okay, here it is. So how do I explain to you, or how do we mathematically understand and make progress on this rich substitution pattern? So we do that by introducing a new object, which we call the propagation matrix. So how do we do that? Well, imagine that we have a direct shock, ZG, like automation, that automates some of the tasks that factor G was doing. And we want to look at the full effects of that. Well, you can think of the full effects of a shock like that applying just like you do in differential calculus. And in fact, I'm going to do this for first order changes, small changes, applying the chain rule. So there is the direct effect of ZG on the wage. So d log wage G changes by ZG. And then there's an indirect effect because there's a further round of changes in factor prices induced by this. And I can write those as the entire vector of wages changes. So this is a vector, this is a row vector. And then I multiply that by the column vector of, sorry, this is a column vector, this is a row vector, of how this changes the task shares. Remember the task shares are introduced? That depends on this entire vector of wages. So, so this is sort of just a definition. But what this definition gives you is that if I then stack all of these G equations together, I can solve for the general equilibrium effect. And as you can see from the fact that there is the d log W here, and then if I stack them together, that'll be d log W here, it's like a fixed point problem. Wages affect wages through the reallocation of task share affects wages. So if I solve that out, for some of you this will look at a familiar form. This is called the Leontief inverse. So it's the identity matrix minus the Jacobian of the task share vector, and then raised to the power -1 multiplied by the column vector of the shocks. And this thing here is what I call, this Leontief inverse is what I call the propagation matrix. Why is that a useful object? It turns out that if you're doing first order analysis, well, not large changes, but just first order analysis, all you need to know is in this propagation matrix. So all elasticities of substitution, all general equilibrium effects are summarized by this relatively low dimensional propagation matrix. And that's where the rich substitution pattern comes in. This propagation matrix does not have constant elasticity. Its elasticities are endogenous. They change depending on where you are in the task shares, etc. And just to emphasize that, the elasticity of substitution between factor G and G prime, which generally, for example, in labor economics is taken to be a constant, for example, based on a CES aggregate production function, it's the sum of two terms. It's the lambda, which is the between task elasticity of substitution, because different factors are performing different tasks. And then it has a term that comes from the changes in the wages of group G prime on the task shares of group G. So if you are a female postgraduate group, I am a male postgraduate group, then there's going to be a lot of competition between us for marginal tasks. So this number is going to be high. Whereas if I'm a high school dropout and you're a postgraduate woman, no competition between marginal tasks. Then we're going to be close to lambda. Okay, so let me skip this. So this is the endogeneity of the macroeconomic elasticity. So in some sense, there are many notions of elasticities here. One notion of elasticity is here. Here I'm assuming that, again, for simplicity, the elasticity of substitution between factors within a task is infinite. They are perfect substitutes, different with different productivity. Then there's a different elasticity of substitution, lambda, which is the between task elasticity of substitution. None of these are the elasticity of substitution at the macro level, which is determined endogenously from this sort of form. Yes? Labor supply, yes. Yes, it does. Labor supply also itself is affected by the propagation matrix, and then it feeds into wages. So all it does is go through wages in a competitive market. So all I need to know is still the propagation matrix, but the equation changes because now the labor supply elasticities come in as well. But I'm not going to present that today just for simplicity. Yes, please. In the inverse of the task share Jacobian. And Jacobian is just a fancy word for the vector derivative of a vector. Okay, so now armed with these, we can start analyzing the different effects of different types of technologies. So let me start with automation, which at some level is the most novel part, but it's also the simplest one to understand because of the, arguably at least anyway, from my viewpoint, the descriptive realism of the framework. I gave already the example of industrial robotics, CNC machinery, software systems. And what it does is that it takes some tasks, and here for simplicity, I drew this as these tasks being taken from Group G. Think of the Group G as the high school graduates work doing some routine tasks in offices or on the factory floor. And these are now taken and assigned to capital. That's why they're in yellow. That's the extensive margin. This, given this AG set, I can compute what we call the direct task displacement effect. So what is that? Remember, what is this brown area here is the integral, that's the task share. So that's the integral of this area with some weights that depend on the productivity. Remember, that was this thing here. So that's, for example, in the specialist case where lambda is equal to 1, the task share is just the area of this. Okay. So what the direct task displacement is that from that integral, I'm going to subtract this area, and then I'm going to compute a new integral. That's what the direct task displacement is. Sorry, I got a minor cough 5.5 weeks ago, and somehow it's left my throat very scratchy. So when I talk, I start coughing. Sorry, I'm not sick, just coughing. I also need to know what are the cost savings, meaning how much money do I save as an employer if I have these tasks performed by machinery rather than labor. And that I'm going to denote by pi g. It's actually pi g of x, and then I aggregate over pi g of x. So those are the only two quantities now I need to know about a new technology, the direct effect and the cost savings. And from there, here is the proposition that shows what the economy-wide effects of automation is. So the impact on group G is I take the G row of the propagation matrix, and I multiply that by the productivity effect, how much output increases, and by this direct task displacement for the entire vector of groups. So this D gamma auto is these D gamma G autos stacked together. And this is a vector because at the end of the day, that's what the propagation matrix says. You're not impacted just by the automation that influences your group. You're also impacted by the automation that influences other groups. Why is that? Well, if we go next to this graph here, once these tasks are taken away from group G, what will happen? Group G's wages are going to start falling. As their wages start falling, now they become more competitive for these marginal tasks, the boundaries, and so they start taking over tasks from other demographic groups. So that's what the propagation matrix captures, and that's why it summarizes all the information about the elasticities of substitution. So that's why here you have this propagation matrix coming in, and that's why the propagation matrix is crucial. And what is the aggregate productivity effect Well, the productivity effects are just these cost savings across different demographic groups, or the automation suffered by different demographic groups, the displacement, and SYG is the output share of these different groups. So if you're displacing a lot of the tasks from a tiny group, it's not going to matter much. And that's the TFP impact. Socio-automation is the name that I give to the type of automation that, just like customer service example that I showed you in the earlier presentation, is profitable for firms, but it's not a huge cost saver. You're a little bit better, but the quality declines a little bit, etc. When that happens, this pi G auto is small. And when that's the case, the TFP effect is going to be slow. So automation is the type of technological change in general that can have small productivity effects, but it can have very large distributional effects precisely because it's impacting the extensive margin of the task allocation. In fact, automation can reduce wages of the impacted group, especially when the propagation matrix is close enough to a diagonal, meaning that I cannot immediately transfer the burden of automation on me to another group, and the technology is so-so, meaning that it doesn't generate a huge productivity effect. So this is why, as I said earlier on, some technologies are going to have a much more first-order impact on the distribution than on productivity, and automation can be like that. Now, I'm not denying here the equation allows for the possibility that automation can be revolutionary. You can have an automation that creates such huge cost savings that output goes up by a lot. But at least it's a possibility that automation can happen without changing TFP, total factor productivity, by much, but have big distributional effects. And because the propagation matrix is here, the negative impact on some groups can spread to other groups. Now, for those of you who are professional economists, you might also notice that the propagation matrix is not in the TFP equation. That's because of a logic like the Halton's theorem, that the propagation matrix captures second-order effects, meaning that after the first impact, there's a second reallocation, a third reallocation, a fourth reallocation. That's why they have the Leontief inverse. But all of these things by an envelope theorem logic are second order. That's why the propagation matrix is not in the TFP equation, but it's in the distributional equation. That's also the same logic as the Halton's theorem. New task creation. Now that's the opposite. Now you're adding new tasks to the production process. This is the area of this thing we're adding, NG, and these are the new economic surplus generated by new tasks, which could be large or which could be small. It's also an extensive margin change, and its impact is very similar to automation, and you can see the impact is the vector of wages is the propagation matrix times the changes that affect everybody. This DLM here comes because of a normalization, doesn't matter very much, and the TFP effect is again. So the logic is very similar. Again, the propagation matrix is not here, but one important thing to emphasize, and this is a key point that again I touched upon in the broader presentation, automation always reduces the labor share. So if all technologies took the form of automation over the last 200 years, we should have seen a steady decline in the labor share. Why doesn't that happen in the data? Well, either automation is not important, which at least my reading is the case. It's not the case, and a lot of data supports extensive automation in the 19th century, early 20th century, and so on. But there's another reason why the labor share doesn't fall, is because new tasks. So these new tasks increase the labor share. So there's a race between automation and labor share. If automation runs ahead of new tasks, then you get the pattern that I showed you earlier on, where labor shares are declining. When new tasks run ahead of automation, then you can actually have the labor share increasing together with productivity. What about labor augmenting technologies? So those are the ones that the previous existing literature, the very canonical literature, what everybody learns,
typically focuses on. Now, the realistic version of that would be we have a new machinery that makes workers more productive in some tasks. So that would be like this. That is completely at the intensive margin. It's completely at the intensive margin because it only makes these workers more productive. It doesn't, in what they do already, it doesn't make them more productive in alternative tasks. So what will happen in this case is that you get a productivity effect again, and this is the change in the productivity of these factors, and that's multiplied by 1 minus lambda. When lambda is close to 1, it's in practice good estimates of lambda are around 0.5. So it's not too close to 1, but it's not too far from 1 either. Those are not very important effects. Actually, this equation, if you just look at this part, it actually exaggerates the effects of the labor intensive margin changes in labor augmenting technologies. Why? Because when I increase this, what I do is that I make type G labor more expensive. When that happens, now they become worse at competing for these marginal tasks, so they actually retrench. They lose some tasks. So these intensive margin tasks don't really have much of a distributional effect because the group that gains endogenously loses some of that gain anyway. And that's why in the case where lambda is equal to 1, this term completely washes out. Substitution and quantity effects completely cancel each other. So it has no distributional effects. It only has TFP effects. So now you see the contrast. Those at the extensive margin have potentially small productivity effects, big distributional effect. The intensive margin ones have big productivity effects, potentially very, very small distributional effects. When you actually, I think we're okay. It's fine. It's work. When you actually look at them within the context of realistically quantitative models, it really doesn't have much of an ability to explain the big labor share changes, the big distributional changes. Whereas I'm going to show you now in the last part of the third part of the presentation, the automation task framework has much greater capability to do that. And same thing for now, it's a little bit more complicated when labor augmenting technologies makes tasks more productive everywhere, but generally similar. Same thing for capital augmenting technologies. So here is taking stock. Now in the equilibrium fully characterized, you can write the wages as an outcome of different types of technologies. Now you can see all of them here. The propagation matrix again is there because it affects it determines fully the aggregate macroeconomic elasticities of substitution. You have the productivity effects and you have the direct task displacement or the direct task reinstatement effects. And now we can see whether it actually does a good job of explaining the data. And what I'm going to do next is I'm going to show you first reduced form evidence, and then I'm going to show you how this whole model can be estimated using the estimates of the propagation matrix as well. So reduced form and then quote-unquote structural analysis. Okay, so to do both of those, I need to measure automation, I need to measure task creation. So both of these come from theory combined with some new data, and I'm not going to show this, but in the theory we can show that under some basic assumption that this task displacement, this gamma G auto, can be written as a product of 3 terms. And this is from the multi-sector version of the model, which I didn't even present, but its I's are now sectors. Omega GI is how important sector I is for group G. So if I'm, for example, a high school dropout, management consulting is not that important for me because I don't get much wage in the management consulting. So these are the wage bill shares. This is the extent, remember I said automation always reduces the labor share. So we can express everything in the labor share change units. So these are the labor share changes in output due to automation in sector I. And then the exposure of different groups to that is a function of who is represented in the tasks that can be automated in those sectors. So in particular, if you are an employee in the automotive industry in the 1990s, whether you're going to be displaced from your task due to robotics depends on what task you perform. If you're an engineer, no. If you're a robotics specialist, you're actually going to get a lot more new tasks and new demand. If you're a manager, no. But if you're a blue-collar worker doing a routine tasks, yes, those are the ones that are targeted. So this RCAG routine is the share of routine jobs that in industry I that group G performs. So this equation is derived from theory, and then we can measure it by using my and David Otter's measure of routine jobs. This here we estimate ourselves, and this we get from census data. And this is our automation measure, and this is the number that I showed you in the previous presentation as well. This is the direct task displacement, what share of tasks that you were doing before you're losing. And I show you here as a scatter plot against the hourly wages of the group in 1980. You see that automation affects especially a lot of the middle wage category. If you're the highest wage groups, these are the college graduates, postgraduates, they get very little automation. If you're the lowest wage group, people who work as home help, healthcare aid, custodial stuff, they're not affected by automation. But if you're a blue-collar worker, these are the ones here, then you're affected a lot by automation. We measure new tasks in the same way. We get data on new titles in occupation. So essentially the dictionary of occupational titles and other data sets like that have for each detailed occupation the things that they do. So if there are new things in that occupation, we associate them with new tasks, and then we say that those new tasks are available to the demographic groups performing those occupations before. So that's what this thing does. So it does use the wage bill share for the group I in occupation, group G in industry I in occupation O, and then we use the share of new job titles that are coming in on waves. And that's what this is. You see that now, in contrast, there are the high education groups that are getting more new tasks, but new tasks are not as unequally distributed as automation. Look at automation. This is very unequal. Goes from above 30% to essentially zero, whereas new tasks go from there's some small groups, you ignore them, it goes from around 32, 33 to just under 24, just under 17, sorry. So it's much smaller range. So then what we do is that we take this equation here, which I derived, and we estimate this equation. First, let me take this propagation matrix to be diagonal. So when that's the case, I don't have to worry about the ripple effects that come from the automation impacting other groups. So for Taner's group, I only look at the Taner's wage. I only look at the automation affecting Taner's group. I'm going to relax this in a second. But let me start there. And then in this equation, I have the productivity effect that goes into the constant because it's constant for everybody. You have these other things like labor augmenting changes. Those we proxy by sectoral TFP or sectoral value added changes and detailed education and gender dummies. So we allow, just like in the skill bias technological change literature, educated workers, less educated workers, women versus men, to have different trends in the labor demand or in technology. So very flexibly. And this is what you get. I'm just going to show you the regression output in diagrammatic form. So this is the task displacement, this is wages, this is the bivariate relationship. No covariates are controlled for. So you see already there's a very strong bivariate relationship. That's, I think, completely impossible to make sense of in the existing frameworks, but it's exactly what our framework predicts. And here is the relationship once I, this is employment. As I said, we do the same thing with employment. So this is a change in the log hours worked for this group, and you see the same thing, which is essentially what Taner was anticipating. You also move along the labor supply curve. In the United States over this time period, it gets less attention, but there's also a huge increase in employment inequality. Low education groups are working much less. Actually, postgraduate graduates are working more than they used to. It's a very interesting pattern. So the model accounts for a large chunk of that. You see the same type of pattern, but reverse for new task creation, exactly like the model predicts. Groups that are getting more new tasks get higher wages, Now, I thought I had already put in the presentation also both this figure in bivariate form and with all the controls I mentioned for sectoral changes and sectoral TFP, skill bias technological change. Now, I don't remember which one I did because the two look very identical. I'm going to show you that in a table format. It's practically impossible for me to know which one this is, whether it's the bivariate one, because they look very similar. So here it is. This is the first column, which shows this relationship, simultaneously automation, task displacement, and new task reinstatement without any covariates. And I just draw your attention that the R square of the model is about 70%. 46% of that comes from automation. 20% of it comes from new tasks. Now, let me not make this very long, but let me now put all of the covariates together. Gender and education dummies, sectoral markups. So we allow markups to vary differently across sectors. We generalize the model for that because that's an important part of the product market evolution in the United States. Sectoral PFP, and the coefficients are hardly badged. And now the model R square is 84%, but a lot of it again comes from automation, about 51%, over 20% from new tasks. What about all of these things that the previous literature emphasized? Markups, skill bias technological change, gender bias technological change. They account for no more than 4% of the data. So it's really about these extensive margin changes. And this is the same thing for employment. There's much more variability in employment that we cannot explain. So instead of 67%, it's 53%. But again, automation and new tasks matter. Interestingly, for this, new tasks play a little bit more of an important role. And that's because there are really some very interesting changes at the top end of the hours distribution. All right. So the final thing I will do in the next 10 minutes or so, and then we can open it up for discussion and comments, is what I just showed you doesn't do justice to the model because it doesn't allow for these substitution between groups. To do that, we need the propagation matrix. So, so the propagation matrix can be written down in more explicit form. In our work, which I'm not going to go over it, we derive the properties of the propagation matrix. It has some nice symmetry properties, and you know the relationship between the diagonals and the row sums, etc. But I'm not going to get into that. But what I'm going to do is I'm going to show you very briefly how the propagation matrix can be estimated. It can be estimated in two different ways. They have exactly the same idea. In some of our early work, we did one way, which is we parameterized the propagation matrix. We did a dimension reduction, and then we estimated it with GMM. Or you can actually parameterize the Jacobian and then estimate that, and then once you have the estimates, you can invert that, or you can do the Leontief inverse. The second one turns out to be more robust, slightly more robust, and it's slightly easier to interpret. So let me do the second. So this is the wage equation now, not written with the propagation matrix, but with the Jacobian on the right-hand side. So this is the Jacobian, or the Gth row of the Jacobian. And then what I'm going to do is I'm going to parameterize the Jacobian in terms of the similarity, meaning that the entry of the Jacobian corresponding to the row for Tanner and my column is going to be how similar the jobs that Tanner and I do and how similar we are in terms of education and age. And then we estimate these things by GMM, and it's exactly the same identification orthogonality assumption that our measures of task displacement and automation are orthogonal to the error term. Okay. We also we could estimate lambda, but we impose it as 0.5 because they're good estimates always in the literature. That's and then we estimate what we impose the between sector elasticity as well which we cannot estimate from this data. The rest we estimate. Now, the estimates make sense. I have them in visual form, but I didn't put it in this presentation. But then once we have the propagation matrix, what we can do now, we can do the full general equilibrium, and that's what I'm going to do. And here is a summary of the general equilibrium for automation. So what I'm doing in this figure is saying, now let me take the same automation shocks that I use in the reduced form regression analysis, but now let me have them run exactly through this equation here. So instead of running a regression, I have GMM estimates of the propagation matrix. I have lambda, I have these terms, so I can just directly look at what the predicted effect on the wage will be. So the only estimation was the GMM, generalized method of moments estimation of the propagation matrix. Once that's done, everything else I have at my hand, and then I can actually do that step by step. I can say, imagine I have the automation, it only has the productivity effect. That's this. Productivity effect is uniform. Everybody's wage goes up by 40%. If the US economy was subject to the automation changes that we saw with robotics, CNC, software systems, etc., from 1980 to 2016, everybody's wage would have increased by 40%. But that's not the end of the story. First of all, automation is uneven across sectors. Some sectors get more automation, some sectors get less automation. If that happens, sectors that get more automation are going to have lower prices, etc., because of cost reduction. That will create some sectoral reallocation. Is that a big deal? In general, it can be. That's the Baumol effect, Baumol cost disease, some of you may have heard. That's a sectoral reallocation story. But it turns out the automation is not big enough to make a huge difference for labor demand in terms of sectoral reallocation. So you get some effects here, but not big. Then I say, now let me add the task displacement. So this panel here adds the task displacement. Now you see a huge inequality. These groups, they didn't suffer automation much, so their wages remains here. But look at these groups. These are the ones that have suffered automation. Their wages now decline by as much as 30%. But that's not the end of the story. This is the direct effect. And then here I add the ripple effects, all of these substitutions working through the propagation matrix. So that has a democratizing effect, meaning that now these groups compete for marginal tasks with other groups, so they pull themselves up, but they pull other groups down. But they can't compete against postgraduates. They are doing very different tasks. And when you do this, now automation explains 41%. My reduced form number was between 40 and 50. So the general equilibrium, completely different strategy, sort of comes to the ballpark, but a little bit lower. Now, let me do the same for new tasks. Productivity effects is here. Sectoral shifts very small. Task reinstatement, it should be. Now, small inequality. The ripples make it more democratically spread out. This explains about 7%. Now, this one is quite a bit lower. In the reduced form, new tasks were explaining about 15, 20%. Now, much lower. Essentially, what that says is the reduced form model was introducing an upward bias relative to the general equilibrium effect. And the reason for that, as I showed you, they're not very unequally distributed. Now, I do the same thing for sectoral TFP, not much, about 2%. Again, productivity effect, sectoral reallocation is now bigger because there are some big differences between sectoral TFP. Not that much of a displacement, and odd ripples, and it's compressed, not much inequality increase. Sectoral markups, nothing. Why is that? Markups actually matter a lot. It's just that sectors whose markups are increasing have very similar labor demand to sectors whose markups are not increasing. All right, summary. I have introduced a new framework, the task framework, the task model, which I think is descriptively more interesting about the production process. And I showed you it makes new predictions about how different types of technologies explain the data. And in fact, it has a shot at accounting for the rich patterns of labor market developments we've seen in terms of productivity effect, distributional effect, wage declines, wage increases, and the rich patterns of substitution between factors in the data. This is very much scratching the surface. There are many things to be done in the task framework. One of the papers I mentioned in the beginning is a handbook of labor economics chapter I wrote with Pascual Restrepo and my student Frederick Kong. It outlines in detail lots of directions for research, some theoretical, some econometric, some empirical, and I non-objectively, from an impartial point of view, not an impartial point of view, I think this is an exciting area for research for many people to participate in. Thank you very much.
Thank you very much, Daron. This is Ahmet Aysan from Hamad bin Khalifa University. I would like to take this is a very good framework for sure. Thank you. It's already published in very good places, and it will open up for future research for sure as well. I wonder about the minimum wage because when I think of Turkey, many of the people are anyway getting minimum wage, and I believe your graphs are quite interesting in that regard. And the minimum wage is not necessarily determined with the market condition. It is quite a political process. And one of the reasons when we talk with the business people, they automate, not trusting the government, because anyway the minimum wage can be quite volatile depending on whether there is election, there are some conditions. So it's better to invest for automation because there is much less volatility there. I know in your model there is no volatility of capital, but are you thinking of kind of considering some volatility of wages and volatility of the capital, and then probably it will even further lead to, if the volatility of the capital is less than the volatility of the wage, probably there will be even more automation, which I believe what's happening in Turkey. Thank you,
Ahmed. That's an excellent question. But as background, Ahmed was my research assistant at the World Bank many years ago, where we worked on this reduced form aggregate production function with HNL across the transition economies. You might remember.
I do remember.
Blast from the past. That's an excellent question, and I think minimum wage matters here and has exactly the effect that you say, which is that if you increase the minimum wage, say for one demographic group, it becomes more expensive, so it makes it more likely that their tasks are going to be either allocated to capital automation or allocated to another group. Very different effects of minimum wage here, because the elasticities of substitution are endogenous. So whether minimum wage is imposed against for a small group or large group is going to matter a lot. But it becomes much more interesting in a setup that we study in a new paper, where we introduce labor market imperfections into this framework. In that case, automation, minimum wage would have an even bigger effect, but it could also be rather a complex phenomenon, because in that framework we also show there could be over automation, because you may actually do automation in order to dissipate some of the rents that some factors are earning. So you can have inefficient automation in that way. But minimum wage would complicate those matters, and we discussed that a little bit, but we don't actually place as much emphasis on minimum wage in that paper. Perhaps we should in the revision. But the important point that you make, uncertainty is very interesting, and in none of the models we consider uncertainty. Two of my students actually, Andrea Manera and Michele Fornino, wrote down a model with uncertainty and automation, but in fact, motivated by the US framework, they went in a different direction than the one you suggested, which is that they thought that labor is more flexible, whereas capital, being specialized capital, is more rigid. So they wrote a model of like a Brownian motion style, where labor can adjust, whereas capital cannot. But another dimension would be exactly yours, where the uncertainty comes from policy. And then that uncertainty could be a force towards automation, whereas for them, uncertainty was a force that slowed down automation. But it's a very interesting direction. Thanks for raising that, Ahmet. Please. Taner also had a question. Oh.
And Austin Technical University. I wonder the generalizability of the model. Your model is based on US data. So what kind of other variables should be added to make it more generalizable for other cultures? This is my first question.
Excellent question.
And the other question is, we all know the importance of the share of labor and capital, and they are responsible for the most critical crisis in the economy in the last century and this century as well. So what are your, in the implication side, your suggestions based on this model, if we can keep the economies globally in balance? Thank you very much.
Thank you. So, two answers to your first question, which is, it will be very interesting, and I don't know the answer. So, in fact, we've been very much motivated by US phenomena, because that's one of the places where many of these things are best documented, and we live in the United States. And a lot of the literature focused on the United States. So our objective, our plan for this handbook chapter was to do empirical analysis for other industrialized nations as well, but we gave up because the handbook chapter reached 120 pages just with the theory, exposition, in reduced form on the US and structural methods. So we didn't do that. Somebody else hopefully will, so that's very important. But second, for developing countries, it's very interesting as well, because developing countries are often receivers of quote-unquote inappropriate technology. So for Turkey, it may be, leaving the issue that Ahmet raised, it may be best to activity, no group would lose too much. But even more importantly, automation done right would have to be combined with new tasks done right. If you don't do that, you're going to lose the labor share, and then when the labor share declines, the tension for shared prosperity is always going to be high.
Thank you very much. So you mentioned in the morning session about Licklider's theory,
Yes.
man-machine symbiosis. So in that theory, he says the tasks which cannot be done properly by man should be converted to the machine.
Yes.
So can be the reason for the failure that they don't follow the theory of Licklider.
Of course. Licklider, Wiener, Engelbart, the three people whose pictures I show. Actually, I didn't show Engelbart's picture, who was an amazing engineer who produced the computer mouse, hyperlink, hypertext, menu-driven computers. They have all fallen by the wayside because the new sort of religion in Silicon Valley is all automation. So they want to automate everything, not just things that cannot be done by humans well.
So can we say that this is an ethical problem which should be regulated by
I
some
think it has
other
ethical
bodies?
implications, but we have to understand it first at the social science or the positive level. But I think it has very important normative implications. And the question of what's the right direction of technology, of course, is a normative question.
Thank you very much.
Thank you. Taner? I think there's a microphone. I have some more.
So seems to me that the automation here seems kind of like falling from out of the sky, where I would have thought that it would originate from the high-skilled it would be some sort of a high-skilled task. So is there like a dynamics that you're doing here, which kind of like looks at the steady state of?
Yeah. So the first paper that, well, it wasn't our first paper that was published, but it was the first paper we wrote on this topic, was published in the American Economic Review 2018, does that. So it is one in which there's endogenous innovation. You can either innovate for new tasks, innovate for automation technologies. There's capital accumulation, and we characterize the steady state dynamics in that economy. But then compared to the Econometrica and the Handbook of Labor Economics framework, it's a simpler thing. There's one type of labor, one type of capital, and to create a balanced growth path, we parameterize the comparative advantage schedules. This paper here, the working paper, we take the menu of automation technologies as given, but with labor market imperfections, the decision of which ones to automate, which ones not to, is a more interesting choice than the one I went through here. But here I simplify, or in the handbook chapter also, we simplify these things. But thank you, that's a great question. And in fact, one lesson of that dynamics that I think you're anticipating is that there are endogenous forces towards automation technology versus non-automation technology. So if you do too much automation, ultimately, it will make more automation less profitable. Why? Because the labor share falls so much that labor becomes cheap. So it doesn't guarantee that there's going to be efficient amount of automation, but there are some forces that might force you towards an interior balanced growth path or interior steady state. But then there are some parameters for which you can go to what we call a horse equilibrium in that model. And the horse equilibrium is after Vasily Leontiev, who said, don't be so sure that man is so indispensable. People thought horses were indispensable, and then they were completely eliminated. So we call that the horse equilibrium. Please, yes. Merhaba Banu.
Banu from Başkent University. I just like to add something to Professor from Ostim University. You always underline the institution's deterioration in Turkey. Do you think that automation increase, if it happens in Turkey also, does it make up, or what kind of effects we see?
Well, I think
Thank you.
That's an excellent question. We are not there yet, meaning the amount of automation is very important, but it's not at a level where capital becomes completely independent or non-dependent on labor. If you come to a stage where automation is so advanced that labor becomes completely dispensable, then I think it will have much more major political economy implications.
It is too early to say something.
Too early, but we may be heading there, so
Okay.
we'll see.
Hello.
Yes, please. House.
Yes, thank you. About the possible government intervention. The government intervention can come in the form of labor injection. Now we are witnessing these kind of injections in developed countries as well, like in Japan. There is some kind of requirements for the corporations to hire some elderly, and this can be thought as a government injection to the labor supply, which is unnecessarily could be done by the automation or the AI. So can we consider these kind of effects as a counterfactual analysis in your presentation you presented?
Absolutely, excellent question. In fact, the framework I present here, I didn't emphasize it. We develop it a little bit in the handbook chapter, but also is useful for applying, for example, to the immigration debate. Why? Because you can easily put labor supply shocks here. We do that in the handbook chapter. I skipped that. And when you do that, you'll see that the effects are going to go completely through the propagation matrix. Because this rich pattern of elasticity is going to significantly expand the different types of immigration effects. The immigration literature is very interesting, but it has all these conflicting findings. Sometimes you find immigration changes capital. Sometimes you find immigration is good for workers, sometimes bad for workers. Well, that's exactly the kind of things that the propagation matrix gives you, because depending on the on how much the size of the immigration shock and the skill composition relative to the available jobs is going to have very different effects. And one place where you can study that very interestingly is actually in Turkey, because Turkey now, I think, has the country that has received the largest immigrant shock in history, together with Colombia and Bangladesh. But I think Turkey has now just exceeded Bangladesh as well. And one of my students who is visiting one of the ministries, I forget, and Bill Kent is studying that, Ahmet Gülek. And in fact, Taner, you should talk to him because he's doing the input-output version of that as well. So there's a lot to be done in that context as well. And Turkey is actually the great place to do it. And it turns out, actually, Turkey has pretty good data for studying this question. Yes, please.
Okay, so I'm a bit outside the scope. I'm a medical doctor and a PhD in bioengineering. So automatization and technology is one of the basic points that have an impact on medicine, I believe. So even I was operating in the morning with a robot. So, I want to ask you, how will this high tech affect the inequality according to the patients? Because we are also have a kind of change from the volume-based patient care to value-based healthcare. So will that cause a very distinct inequality between the patient populations, or how will that affect the future of medicine?
Well, excellent question. And I think the answer is it depends. You know, sometimes these topics, when I talk about them to a broad audience, I say there is good automation, there is bad automation. If you over-automate, if you take, for example, away from the judgment and the wisdom of the surgeon or the medical doctor, that's bad automation. But good automation can complement the doctors, can reduce costs, and if it goes hand in hand with new information, new capabilities, I think it can do things much better. So I think the right use of robotics in surgery is good automation. But another aspect, is which the US has had real problems with, is using automation in healthcare to expand availability. In Turkey, and I'm outside of Turkey and it's not my area, the healthcare sector is not my specialty, but access to healthcare has improved quite considerably. It's become more democratized. So in that sense, it's become more equal in some ways, but there is a danger that as it becomes more high-tech, it's going to become very unequal again, because it's going to create a two-tier structure where only some rich patients can get access to the best technology and some cannot. So I think there are a bunch of issues. In the US, it's a more futuristic scenario, but I think the big nexus for that is bioengineering. So there is a danger that bioengineering is going to become sort of a very expensive service for very rich patients, for example, in choosing genes and very expensive treatments for life extension, and not available to the rest for even more basic public health. So there are a whole host of normative and positive questions within that context.
Thank you.
Murat Bey.
Professor Acemoğlu, thank you very much for being with us again. The propagation matrix, what happens when it is time dependent? And in particular, can it explain what will happen to the overall unemployment, which is a big concern for everybody else? And also with reference to this very, let's say, well-known idea of Professor Schumpeter, of how these things can be matched, let's say, with the idea of creative destruction on the product side, on the sector side. I know you are looking at it from the labor side, which he didn't do. He did the other side.
Yeah.
And what happens when the product markets are monopolistically competitive? Not competitive, but monopolistically competitive. That means the markup structure will change completely. And that has a bearing, of course, on the sharing of the returns in terms of the capitalists and everybody else and the workers. And last thing is, if you have time, what does all this tell to the developing countries?
All sorts of excellent questions.
This was all for the US.
All sorts of interesting questions. I think this is why I emphasize there's a lot to be done in terms of research. So making the propagation matrix time dependent is very straightforward and very tractable here. In fact, it is already time dependent. I just suppressed it because look at this equation here. This entries of this propagation matrix come from this Jacobian here, remember? This in itself is time dependent because as wages change from period to period, you are already shrinking or expanding these sets. So different patterns of substitution is going to come. On top of it, there might be other factors that make it time dependent. So that's very easy. Now, what we do in some of our recent work, but we need to do much more of it, incorporate this with more realistic models of unemployment. Not just labor supply being endogenous, but more realistic models of unemployment. So there, it's not just the propagation matrix, there's a sister matrix, there are two matrices that determine everything. One is about labor market imperfections, the other one is about propagation. And both of those will be time dependent, and then that hopefully will contribute to an empirically more high fidelity, interesting model of unemployment dynamics, but that hasn't been done. In terms of the product market, absolutely, that's very interesting, but we haven't done that. As I emphasized here, we allow for markups to change, but what we don't allow for is endogenous markups. So an interesting model, which we explore briefly in the appendix of one of our papers using French data on firm level data, is that actually automation will change markups. Why? Automation takes place, if you look at the data, mostly in large firms. They already dominate the market. So once they do automation, their costs decline, and their competitors, the smaller firms, don't have the same cost increases. So it also increases their markups. So there's an endogenous markup change, and that is going to lead to a lot of things. And I think that's one of the concerns with, for example, the field of AI being dominated by just two firms, for example. So that's a very interesting set of phenomena that are going to emerge. Yeah, so that's the case I'm talking about. That's why the markups endogenously change. So the case we consider there is a nested CES demand structure, but you could do it with other things as well. So your productivity increases, your costs decline, mine doesn't, so your markups will start increasing relative to mine. And at the same time as your markups increase, you're also going to start capturing more of the market because your quality is also improving. So it really changes the nature of the market. And then finally, for the developing economies, I think it goes back to the earlier question from your colleague. I think that's the first order thing. We discussed this in the part of a chapter in Power and Progress, İktidar ve Teknoloji. So you have to sort of incorporate this issue of inappropriate technology in what is produced in the US. Is that for the US's interest or for the world's interest? I think, for example, two of my students, Jacob Moscana and Kartik Shastri, have written a series of papers that are really nice on agricultural technology, showing that because agricultural technology originates in the US, France, Germany, Switzerland, it's very inappropriate to the conditions, to the seeds, and to the pathogens that exist in the developing world, and that causes a lot of low productivity in agriculture, especially in sub-Saharan Africa and also in South Asia. So lots of interesting issues, and exactly like you suggested, it's a normative as well as a positive question.
Do we have any questions? Okay. Oraya götürür müsün?
Hello again. Thank you very much for your answers, dear professor. So when I listened your lecture, it stimulated some thoughts in my mind. For example, if I call
that's my purpose.
Thank you very much. So if I say it's the apple tree theory, so when the evolution of this AI in the industry, so the digital technologies, are reducing the importance or the share of the labor in those industries, then they are becoming self-competent. So they are doing all the business themselves like an apple tree. So what do you think about this as a
So
vision?
I mentioned to Taner the horse equilibrium. That's exactly how the horse equilibrium happens. When you have more and more automation, you don't need labor anymore, and then both the investment goods and the final goods can be less labor intensive. That enables you to build more capital, leads to more automation, and that's the self. So yes, that's
some kind of organic structure.
some
So
kind
is,
of
is it
structure.
good or bad?
Well, again, it depends on your normative principles and the richness of the model. So here, the model I have is a competitive equilibrium without any labor market imperfection. So the equilibrium is by the first welfare theorem Pareto optimal. So if all you care about is Pareto optimality, you don't want to interfere here. On the other hand, if you care about distribution, or if you have other concerns like labor revolting and creating instability or a revolution, you would want to interfere. But if you enrich the model with labor market imperfections, then there is actually excessive automation, and you may want to interfere for efficiency reasons as well. So, but I think the normative questions are more important, and that's also related to the new book I'm working on as well. Thank you.
Thank you.
Thank you very much, Professor. I will make a general remark, in fact, and ask a general question because I waited the end of the technical questions. In fact, some centuries ago, we faced a very high need of labor force, and then humanity or strong countries tried to solve this through slavery. Still, we are paying the the price for it. I mean, that was a humanitarian solution, and there was so many negative effects. Now, of course, we have automation, artificial intelligence, and of course, there will be various social implications which you are already searching for. I would like to ask, what is your insights? How we can cope with this and with minimum bad effect and high positive effects? You mentioned it increases productivity, which is the main thing, but some circles are proposing, of course, with other reasons as well, to drastically reduce the population, which I don't agree, to be frank. But what is your insight? Some countries are reducing work hours, some are flexible hours, some are, I think, training for the need of the future markets. I would like to hear your personal insights about that. Thank you very much.
Well, thank you for your question. First of all, I think part of my general answer is what I gave in the morning. We need a balanced portfolio of technologies, not just target automation, but target many things, especially providing better information to workers. Second, the issue of demographic change is first order, and it's coming. One thing we can forecast is demography, because you know what the future workforce is going to be. Fertility patterns are relatively well understood. So we know the population in the West is going to drop significantly. The world population is going to plateau in about 30 years or so. Even countries like Turkey are going to start reducing their populations and aging. Now, aging creates a lot of challenges, and economists have generally viewed it as a big burden. My work, actually, a different branch of work that I did with Pasquale Restrepo, also doesn't find any support for that, especially if countries that are aging can invest in the right technologies, including automation. They can adapt quite well, and Germany and South Korea have done so. Now, China may not be able to do it because its aging is even more rapid than South Korea, but being technologically at the cutting edge is important. That's a very important lesson for Turkey. As to the current proposals for reducing work hours or universal basic income, I don't think they are permanent solutions, because you're not going to create a happy society by creating less and less work and more dependencies. So that's why it's so important to redirect technology towards things that are good for workers. Thank you.
Professor Hacımoğlu, first of all, thank you very much for giving us the opportunity to listen to you here. Welcome again. in your papers, as you noted, when automation yields only modest productivity gains, the elite may respond by reducing redistribution and making fewer democratic concessions. However, as automation progresses to a point where labor becomes irrelevant, largely irrelevant, there is a risk that the elite might choose to bypass democratic institutions altogether. Given this dynamic, how do you envision the role of policy in balancing the productivity benefits of automation with the need to maintain democratic governance and social cohesion? Specifically, what regulatory strategies could be effective in preventing elite from reaching a threshold where they find it advantageous to abandon democratic principles?
An excellent question, and this is why I said there's a lot of future research to be done. Those are all open questions. The kind of model that you have in mind, a very draft, sketchy form of that is in a section on a paper I wrote in the Handbook of AI Governance, where redistribution and democracy may change as a result of automation. And I have ongoing work with another one of Taner's colleagues, Arda Gitmez, on endogenous automation and labor power and labor negotiation. I think, but the issues that you raised go beyond those, so I think excellent questions to explore.
Okay, it will be the last question, I think.
Thank you.
Thank you for QA part. Actually, I would like to ask you a question for your model, and maybe I can ask you one more thing about it. It seems, I think, impulse response functions with this way, because we are trying to give it any shocks in here automation, and we are looking to its output. With this way, can we compare with a financial crisis and this situation? And the last one, can we say actually you are building up in the first part of today's course, I mean about your book, you said social technology, and we saw again, can we say US is a social technology for this period, I mean 1980s until to 2016? Thanks so much.
I did not emphasize that. Excellent questions. Thank you very much for asking them. Let me answer the second one. I did not emphasize that again. Perhaps I should have. That's exactly what we find here in those quantitative exercises. We find that while automation has these huge effects, its TFP impact is minuscule. So US TFP increases by like 40%. Only about 1/10 of that can be explained by automation. So there's been a lot of automation investments, but its returns in terms of TFP are very small. Now, of course, there may be reasons for doubting those numbers, etc. There's some issues, but I think that's exactly what we are finding. In terms of the impulse response functions, you're absolutely right. Putting your question with Murat's, the time-dependent propagation matrix actually gives you an impulse response function. So over time, you can trace these effects, and that's very interesting. Unfortunately, when we estimate the propagation matrix, it's very data intensive, meaning it requires measurement error is very damaging for that because we're asking a lot from the data. So we've tried to do that on shorter horizons. We cannot do that. It becomes very noisy. So we're pooling all of the data to do that. So we're looking at long differences from 1980 to 2016. But with other data sets, it might be possible to do that, and that's going to be very interesting. But that's, again, future work. Thank you.
Dear Professor, please stay on stage. End of this program, our rector will present you in informative.
My fault.
Yeah, you're welcome. For your informative presentation, I would like to thank you, our guests and dear Professor. Yes, Professor Muratlik. Thanks so much. With this way, we are ending our program. Thank you for your attendance and take care of yourself. Goodbye. Teşekkür ederim. Ayaklarınıza sağlık.